Now that we are done with average velocity, we'll talk of constant velocity. The difference being in average velocity, the velocity was not the same for the entire journey. However, in constant velocity, the velocity will remain the same for the entire due course of time. We'll be trying to address two learning goals in this video. The first one being to understand how displacement time graph would look like when the velocity is constant. The second one is to understand that the gradient of displacement time graph actually provides us velocity. In order to achieve these learning goals, I am going to use a video wherein a girl runs up a hill. As I just told you, this is the video which we are going to analyze to understand how displacement time graph would look like when the velocity is constant. It is a given that this girl is running at a constant velocity. As I had already told you, the first and foremost step in solving any problem to do with this unit is to define the coordinate system. So as you can see, I have made a picture of the inclined plane or the hill which the girl is running. And what I have decided to do is, I have decided to take the direction in which the girl running to be positive, and the point where she starts to run to be 0. So there is an option in the video which I'll show you shortly, wherein I can have a ruler kept over the video. So what I'm going to do is, I'm going to ensure that I will start making note of the positions of the girl right from 0 meter. As I just told you, this is the ruler I was talking about. So what I'm going to do is, I'm going to rotate it such that I would place it this way. And I also have the feature of a stopwatch. So I'm going to reset it to 0. Basically, I'm going to try and collect data which are going to be my displacement versus time. So let me play, or rather move the videos. Yes. Now this is my first data point. So I'll reset it, and I am going to ensure that our center of mass is aligned to the mark which I am interested in it. So to edit this, I will be calling this as t in seconds. Okay, time. This will be t. This will be displacement. Unit is meters, and the symbol which we use for displacement here is s. So the time now is 0, and her position is also 0. I'm looking at a center of mass somewhere. The pink t-shirt which she's wearing. I'm not looking at the legs or anywhere. I'm looking such that her chest is aligned with the 0 meter mark here. So which means that's 0. So let's try and collect the next data point. So I'm going to move frame by frame again. You can see the clock ticking as well. Okay. I'm going to stop here. So now she is at 1 meter mark, as you can clearly see. It's +1 because I've assumed that the direction in which she's running to be positive. The time is 0.2042 seconds, 0.2042, right? So let's continue to do that and play and stop them so that we can, right? So this is 2 meter mark and the time is 0.4167, 0.4167, right? So I've collected the rest of the data using the same process. So you can see all the 6 data points over here. So you've got time across x-axis and the displacement of the girl running uphill across the second column. So now what I'm going to do is I am going to plot the data here. So we have time across x-axis. We're not worried about the uncertainty now. And we have displacement across y-axis, done. I'm going to curve fit it and try AX, linear proportionality. So you can clearly see now that the displacement time graph is a straight line making an angle with the x-axis. Now I would like you to keep a note of the A value, which is the gradient here. It's 4.934. Now we know how the displacement time graph is going to look like when the velocity is constant. So we know that this is going to be distance in seconds. This is going to be displacement S in meters. It's going to look like this. And if you quickly realize that the velocity time graph, the corresponding velocity time graph is going to look like this. Velocity v in meter per second, it's going to look like this, because if you remember I told you this is about constant velocity, which means the velocity is the same with respect to time. Now from the graph which we found out from the data points which we collected, we know that the gradient of this graph is going to be 4.934. Now this number is what connects to the second learning objective. Now let's quickly try and understand what is gradient. Gradient is nothing but, in mathematics, it is nothing but change in y by change in x. So over here from the graph I have the gradient. If I have to write it in terms of the values which you have plotted in this graph, I have change in y to be nothing but displacement by time taken. So we know that displacement by time taken is nothing but velocity. There is one more way of understanding this with respect to dimensions. Now, if you look at the unit of this gradient, we know that the unit of change in y will be meters since we have displacement in the x-axis. And we know that the unit of time or change in x is going to be seconds. So, which means the unit of gradient is actually meter per second, which is also the unit of velocity. So the unit also corresponds to the meaning behind the gradient of displacement time graph. To summarize, the gradient of displacement time graph provides velocity.